Hi, this is Professor SGLee at Seongyungan University. Today I'm going to talk about the English version of Introductory Mathematics for AI. It starts with the basic mathematics for AI, then next matrix, then optimal solution, calculus, and statistics. Then with those knowledge, we learn principal component analysis and artificial neural network. The unique feature of this book is it is written for any high school student or a high school graduate. It starts with the functions and its graph, particularly the graph of polynomial functions. If we can draw the graph of polynomial function, we can find the solution of equation because the solutions intersect the x-axis. So we can zoom it those intersections to find approximated solution of it. Same thing for the rational functions and trigonometric functions and exponential and logarithmic functions. We can draw the graph of these functions without much difficulty with a simple Python-based command plot. Plot command give us the graph of these functions and composite of these functions, which means we can find solution of most of the equations. Solution of most of equations that we have ever learned. Okay, just draw the graph, then we can find the real solution of the graphs. And that means we can, when we have a matrix, then we can find the characteristic polynomial of a matrix, then find the solution of the characteristic polynomial of a matrix, which is the eigenvalue. Okay, if we have a m by n matrix A, then the matrix A transpose A is an n by n matrix. It always has a real eigenvalues, okay, and which is the singular value, which has a will become the source of the singular value of the matrix m by n matrix A. Okay, anyway, we start with the very basic thing: draw the graph of a polynomial, then find the approximated real solutions. And then we run matrix operations, matrix product, matrix addition, matrix subtraction, etc. Then we run low reduced echelon form of matrix A and augmented matrix A, which will give us the solution set of a linear system of equations. And we cover that, and we also introduce the inner product to find the cosine similarity of given two vectors. And then we run one of the best possible solution, which can be a least square solution. Okay. We use the matrix product to find least square solutions. So we run finding a suitable curve for a data. Curve fitting can be done here. Then we run singular value decomposition of a given m by n matrix, rectangular matrix. Okay, can by the theory and also by a simple command of find SVD. And then done limit of function and derivative of function, which lead us the local maximum and local minimum. With those knowledge, the gradient descent method will be covered. Then in part 4, we learn the counting techniques and probability and random variable and expectation, variance, and standard deviation, and to read the covariance matrix. So at this point, the student will be able to find a covariance matrix from a given data. With all the earlier knowledge, will be enough to understand the principal component analysis and rank reduction. If you understand the principal component analysis, the next thing is a backpropagation algorithm and artificial neural network. And the course will be closed with the example of artificial neural network, which is the handwritten numbers detection using artificial neural network. Okay, here we start from week 1 here like this. Yeah, basic math for AI in week 1. This is just one page, so it should be covered in one lecture, in 1 hour or 2 hours, maximum 3 hours. So each we have a 14. It will be enough to cover a whole textbook in 14 lectures. Maximum 1 or 3 hours each. Here we start with the functions and its graph like this. Functions and graph like this. If we have a polynomial, then we can plot the graph on interval -3 to 8 like this. Like this. We can draw the graph of the same graph in the interval -13 to 28. If we draw this graph from -1 to 6, then it means we can magnify the graph like this. We can have a bigger graph. Okay. Similarly, same command plot work for the rational functions and trigonometric functions. So we can find the intersection and we can magnify to find the intersection here or here. Okay, tangent function and also exponential functions and logarithm functions can be plotted in the same way. So basically we can draw all the graph. And this web address gives us better, more interesting features like this. If we can draw the graph of it, so we can from here we can change the coefficient to see the changes of the graph. We can maximize, we can zoom in like this, we can zoom out like this. Okay, so we can, if you want to see in detail we can zoom out like this. Here, if you wanna find the if you wanna draw the graph of heart, all students can draw the graph, because in the calculus class we learned many interesting graphs. Okay, so we can change the coefficient here. Is in this graph is given when a is equal to 12, b is equal to 8, and c is equal to 1, and in this range. And also, when time t changes, it shows how it moves. Since we have learned functions in the calculus, we know the many equations of functions. Okay. And we can draw the graph of it as an implicit function, or a parametric function, or polar equations, and etc. And we can draw many interesting graphs as well. As you see, the equation gives us the graph of heart. And from here, we can find the area of this, and we can rotate it to find the volume of it. If we want to save this, we can save this image as this, and then you have the image GIF file of the image that you generated. If you change the coefficient, you will have a different graph. And if you can rotate it, then you can have a three-dimensional object. So you can use it for 3D printing. Okay, and since we have learned the many equations, then there are many things that we can do. And also, for Riemann sum, in the calculus, we have learned finding the area underneath of the function. If we find the animation, if we can change, we can make n bigger, then we will have a more close answer of the area. Okay. And here we can see as n goes bigger, and we have as n goes bigger, we will have better and better approximation of the area. This gives an idea of the integration for finding the area of it. And all those things can be done. Also, the interesting graph, there are many. For example, for flower, this is the equation of flower, like this. Yeah, we can see the blossom as time t goes. We can see the flower blooming as time t moves when a is equal to b, b is equal to -5, and c is equal to 4.5. Okay, here. So with this, we can find the area of the surface of a flower and leaves and etc. like this. So you have learned how to find the area of this type of the flower of 4 leaves and area inside of it, etc. And we have learned these equations, and now we can draw the graph of it. You can we can use those in a source, view the source, then you will find how we can draw the graph of it. See? This is the core code of it. And if we go anywhere, any Sage Cell server or my lab, then we can use many different languages. Here Sage is a Python-based language. Then we will see the exactly same thing. So the student don't have to know the code, even though they don't have any background of learning the code, still they can use the mathematics that they have learned. Okay, and here, and this so solution of the equation. Yeah, this is the typical way of finding the solution of the equation. The students have spent a lot of time to finding this, but if they can draw the graph of it, they can they know they can find it. And this is the way that they have learned. They solved it by hand or by code. They do the same thing for the complex one, and this book know how to handle this with a simple code. And for the polynomials, even for the complex functions, the composite functions like this, polynomial and exponential functions and trigonometric functions all mixed up there, still we can draw the graph of it. Then we know this equation has at least two solutions. If you can zoom in here and here, then we can find the approximate solution like this. If we plot it in zoom, then we know the solution is in 0.2.19, near there. And but with the find root command, we can find the exact solution if we give the proper interval. And the other one too is 1.084. Okay, then I ask my student as an open problem to find the approximate solution to various equations from other textbook that student ever used from the elementary school to the college. Yeah, they will, if they can draw the graph of it, they know where is the solution, and then they can real solution. They can by zooming in, they can roughly find the approximate solution. And this gives kind of the idea of how we use the computer and how do we make a code to have an iterative solution, to find the iterative solution. And then we may take a look chapter 4, for example. Here, in here we learn the matrix linear algebra part. Solution set, finding the solution set of a given linear system of equations, and basically Gaussian elimination. So, so finding the augment matrices from a given linear system of equation, and find then this solve command give us a solution that we found by hand. But Gaussian elimination give the whole the details. RREF of augment matrix of AX is equal to V gives the same solution that we are looking for, and solve right solution gives the same solution like what we have. So from here, with the code, even though students haven't learned any coding, still they can use it for any linear system of equations. But some linear system of equation has infinite many solution like this, then I will teach it how to handle it, like find the particular solution of AX equal B by code, solve right, then find the general solution set of AX equals 0 by using the kernel command to find the basis for the solution space, and then find the whole set of solution as a solution set of x0 plus s, which is the span of those basis vector for the solution, the space of AX is equal to 0. So because this code only gives the one solution among the infinite many solutions, but also, and here this RREF shows it has a 0 row in RREF, which means it has infinitely many solutions. But also, we will face that there is no solutions. So we teach what RREF means here. So to give the criteria for the unique solution and infinite many solution and no solution. And what we covered here, so students can have a confidence to find the solution set for any linear, any given linear system of equation. And then what we're gonna learn next is we're gonna find a best possible solution. Basically here, the least square solution for a given problem. Okay, so open problem ask our student to practice to explain how and what we can determine for a given system of equation with a unique solution or infinite many solution or no solution. So with this discussion, the student really understand because they can compute and they can see the output from there with their code. After that, we run the singularity decomposition. Here, LU, QR, and singularity decomposition. Here, for a given n by n matrix A, the singular value decomposition can be found and defined in this way. Here, if we can find the singularity decomposition, then we can talk many things. We can talk many interesting things. And first, ask student to find the singularity decomposition of this as an example. Then it has all the explanation, but here in code, we can find the S sigma and V, U, V, U, and sigma respectively, like this, to have and the sigma here, and product of those gives us this U sigma V transpose is the same as the original matrix A that shows it. And the above algorithm can be done by this summarized as a SVD command. With this simple command, instead of those 10-20 lines of code, find the SVD of A, give us U, S, and V, like this. U, sigma, and V. And U sigma V transpose is the matrix A itself. Root 3, 2, and 0 here. Like this, very small number here. So students can practice this code for any n by n large size matrix. So I ask a student as an open problem, find the SVD of matrix that students can find any other book, large excuse me, using the above code. So after this short one-page lecture, the student after their enough discussion, they can really understand. They have confidence. Excuse me. They can have a confidence to find the SVD, and they start to understand the meaning of SVD and power of SVD. Why they are talking about these open problems. It will take about a month. A month. Then a month of learning and doing and sharing their output and discuss on these particular open problems give them a good intuition of the mathematics. Then they learn the calculus and in week 7 and 8 to understand the local maximum and minimum like this, find the derivative and plot it. So they see local maximum and minimums are here, and they learn the application of the derivatives, and then in this one page they start to learn gradient descent method. Like this. How this is looks like Newton's method, but a variation of it. And this algorithm shows how this algorithm works, and there's an open problem to discuss. Okay, and in week 12, they start to run the PCA. Here, dimension of reduction PCA. Here, from the given data, so they build up a data matrix, and then find the centering that matrix to be a mean-centered matrix X tilde. Then find the SVD of S tilde like this, and you can see if you let US is equal to G, then G can be written, G looks like this, and if you choose the first K columns of U and the first K by K submatrix of sigma, then we can define GK. If they understand the meaning of singularity decomposition, then when we choose a very small number of K, still the nature of the matrix of G and GKs are quite similar. So this gives us the intuition of the possibility of the dimension reduction of a given data matrix. And then example really deals with the larger matrix to adopt this algorithm to find the principal component analysis, and it the code shows how PCA really works. So the student had an open problem to discuss and apply this PCA to their own data in their own majors. And these start sections can be skipped, but the students are recommended to read to understand more detail of the proofs in the process of a principal component analysis. Okay, and then and these are the kind of structure that I tried to explain, and it worked well in a very short time because it has code in it and the lab in it in each week in one-page lectures, and so they can really read it and do practice it and change the data, and so they can practice any data or matrix or function of that they have treated before by hand to be simply visualized. Okay, I think that will explains And also, okay, I will talk about Chat GPT later. Thanks for listening.